Hello and welcome to the podcast on lead-acid batteries by Ramesh Natarajan. With industry experience of over 42 years, Ramesh helps battery and battery-related industries with technical inputs and provides solutions to typical problems faced by manufacturers, service personnel, as well as users of batteries and related equipments. Do visit www.rameshnatarajan.in to stay connected. Enjoy the session.
Hello and welcome to this episode of my podcast. Once again, I have another interesting case study for you. A battery manufacturer making automobile batteries faced a problem with self-discharge of his batteries. This issue started to arise after he began exporting his batteries. Join me as I walk you through the various steps before I zero in on the problem caused by an unexpected reason. This thrilling episode will make you assess your process too. This is another unmissable episode for all lead-acid battery manufacturers. To solve this issue, I went through the various processes of his battery manufacturing and the battery design parameters. The standard operating procedures, that is SOPs, were well established and his quality control personnel were well trained. I noticed that both his production and quality personnel were committed and they followed the instructions and procedures. I also realized that the material specifications were precise and aligned with the requirements. The alloy composition was as per industry norms and the specified alloy was suitable for automotive batteries. The grid design was robust and the machines in this department also produced consistent products in the casting department. The paste mix chemicals were also not a cause of concern, with mixing and curing processes well set, documented and monitored. Similarly, there was no reason for self-discharge due to assembly design parameters. I checked the voltage drop possibilities that can arise due to bus bar thickness, plate lug cross section, pillar size, etc. I proceeded to the acid filling and charging section. The calibration of all meters and equipment was valid. The control and monitoring of charge current, current density, AH input, etc. were all computer controlled. The deviations to be made based on temperature variation due to seasonal changes were clearly defined. The operators in this department seemed well versed in equalizing specific gravities and electrolyte levels and relating the specific gravities to temperature before disconnecting the battery from the charger. This particular battery manufacturer had incorporated a discharge step during the initial charging, which is a good practice. I found nothing in the battery charging department that could be a possible cause for the self-discharge. The only department left was the packing and dispatch department. As a routine exercise, I visited this section without for a moment hoping that the solution to the problem was there. Batteries were washed, appropriately dried, wiped clean and moved on a conveyor. They were then shrink wrapped before being packed in boxes. It is the activity before shrink wrapping that caught my attention. A group of workmen opened each vent plug and put some tablets in all the automobile batteries. On inquiring, I was told that these were sodium sulfate tablets. Since the batteries were being made for automotive applications, I told them these sodium sulfate tablets were unnecessary. I was sure this was the only cause of the battery's self-discharge problem in this particular case. As per my usual working style, I did not want to impose any change. I firmly believe that battery manufacturers must convince themselves that any change is for the better after validating and verifying it. I suggested that a batch of 25 to 50 batteries may be tested without sodium sulfate for battery capacity, self-discharge, and various parameters with a similar quantity of batteries that contain sodium sulfate. I also shared with this battery manufacturer an extract from Pavlov's book, in which, in the fourth paragraph of chapter 3 on page 159, he mentions that adding sodium sulfate accelerates the battery's self-discharge processes. For the benefit of the listeners, I am quoting the relevant paragraph so that this matter is understood in the context of this case study where the stoppage of sodium sulfate solved the self-discharge problem. I now quote from chapter 3, page 159 of Pavlov's book. A commonly used electrolyte additive in AGM type of VRLA batteries is sodium sulfate, Na2SO4. This compound is introduced in batteries designed for deep discharge cycling and low temperature operation modes. Sodium sulfate acts as buffering agent and keeps up the conductivity of the electrolyte. As a result, the recharge of batteries after deep discharge improves significantly. This electrolyte additive has proved especially appropriate for batteries in remote photovoltaic systems located on high mountain peaks. Unfortunately, sodium sulfate addition facilitates corrosion of the grids, especially of the negative plate lux and of the connecting strap made of lead tin alloy. This adverse effect can be substantially mitigated by addition of selenium to the grid alloy. Moreover, addition of sodium sulfate accelerates the self-discharge processes in the battery, so this compound should be added only in combination with other additives that would suppress the self-discharge effect of sodium sulfate. Unquote. Battery manufacturers using sodium sulfate for automotive battery applications and facing the problem of self-discharge may conduct tests on batteries without using sodium sulfate, and then they can decide to discontinue the use of sodium sulfate. I feel it's not necessary to use sodium sulfate for automotive battery applications. I do hope this episode was useful. Thank you for tuning in.
Please do visit www.rameshnatrajan.in. Keep yourself updated about our new releases by hitting the subscribe button.